You're all welcome to another section of our integrated science class. We're going to continue with electricity. In the previous section, we looked at electric circuit. We said that an electric circuit is a complete unbroken path along which electric charges move to produce current. We looked at some components of an electric circuit, the symbols of the components and their functions in a circuit. We also continue to look at the arrangement of the components in an electric circuit. We said that the components could be arranged in either series connection or in a parallel connection. We went on to look at arrangement of some of the components, such as bulbs, cells, and resistors. We ended the section by giving an assignment that you're supposed to give reasons why appliances in homes are usually connected in a power arrangement. So today, before we start today's class, we're going to look at the reason why wiring at homes is usually in a power connection, and then we will continue to look at some important definitions, and then we also look at Ohm's law, and then that will usher us into related questions, that is calculations. So first of all, let's take these notes, that is with respect to the assignment I gave in the previous section. So wiring in homes is carried out in parallel connection in order to one allow frequent switching on and off of electrical appliances without a breakage in the circuit. And then two, allow bulbs to receive maximum voltage to produce highest intensity of brightness. Okay, so this actually the solution to the assignment I give. Reasons why wiring in homes is carried out in parallel connection, or reasons why electrical appliances at homes are connected in a parallel connection. So the first reason is to allow frequent switching on and off of the appliances without a breakage in the circuit. So what it means is that if your appliances such as your fridge, your television, the bulb, if they are in power connection, the fact that you switch off your television does not mean that the fridge and the light will go off. Or it means that if both the fridge and the television is on and then you switch off the fridge, it doesn't mean that automatically the TV will also go off. So that is the most reason why the appliances or wiring in homes is carried out in power connection. So that when one appliance is switched off, the others can still be switched on. And then also, power connection allows bulbs to receive maximum voltage so that they can produce the highest intensity of brightness. So this is the solution to the assignment I give. Now we're going to continue today's section by looking at some important definitions. Definition of some terms. The first term we're going to look at is what we call potential difference. Potential difference. Which is shortened as PD. So in electricity, if you come across the word PD, it is referring to potential difference. It is referring to potential difference. It's referring to potential difference. Now, when we're looking at electric circuit, I told you that electric charges flow through the conductor in a circuit. It is when the charges are flowing or they are moving, that is when electric current is produced. Now, the work that is done in driving a unit charge to produce current in the circuit is what we call potential difference. So the work that is done to drive one electric charge through a circuit to produce current, that work is what we refer to as potential difference. So we said a potential difference, it is a work done is the work done in driving a unit electric charge driving a unit electric charge through a conductor to produce current in a circuit. So the work done in driving a unit electrical charge, electric charge through a conductor to produce current in a circuit. That is potential difference. The unit of potential difference is volts. So it is measured. It's measured in volts, which is represented as V. It's measured in volts. The second definition we're going to look at is what we call electromotive force. Electromotive force. Electromotive force is also shortened as EMF. So when we come across EMF, and then we are referring to electromotive force. Now, in connection to PD, I said that the work that is done in driving a unit electric charge through a conductor is so referred to as potential difference. Now, for you to drive, for that electric charge to be driven through the conductor, a force is required, or a force is needed. So the force that is needed to drive a unit electric charge through a conductor is what we refer to as what? The EMF. The work that is done in driving the unit electric charge is the potential difference. But the force required in driving the unit electric charge is what we refer to as electromotive force. So it is the force required to drive a unit electric charge through a conductor to produce current in a circuit. Okay, so that is EMF, the force required to drive a unit electric charge through a conductor to produce current in a circuit. It is also measured in volts. It is measured in volts. Third definition is voltage. Voltage is represented as V. Voltage is represented as V. Now, we say voltage is the measured potential difference across the terminal of a cell when a circuit is closed. We've looked at types of circuits. I talked about open circuits and then closed circuit. I said that when a circuit is open, meaning that the key or the switch is open, electric current will not flow through the circuit. But when the key is closed, we said that the circuit is closed. It is when the circuit is closed, that is when current will flow through the circuit. So when current is flowing through a circuit, the potential difference that is measured across the terminals of a cell in the circuit is what we refer to as what? The voltage. Is what we refer to as the voltage. So voltage is, so it is the potential difference measured across the terminals of a cell in a closed circuit. So voltage is the potential difference measured across the terminals of a cell in a closed circuit. So this is very important. Closed circuit. In your definition, the closed circuit there is very important. Now, the unit of measurement of voltage is also volt. So it is measured in volts. As you can see, all these three terms, PD, EMF, and voltage, they are all measured in volts. They are all measured in volts. In core class, actually, when it comes to calculation, all these terms refer to one thing. We refer to as voltage. So in core class, when we start with calculation, I have to measure, calculate PD. Indirectly, you are calculating for voltage. If you are determining EMF, you are calculating for voltage. The last definition we're going to look at is resistance. Resistance. Resistance is represented as R, big R. When we're looking at the components of a circuit, we came across resistor. And I said that this resistor measures resistance. So what is resistance? The resistance is the force which opposes the flow of current in a circuit. So when current is flowing through a circuit, there is a force that tries to hinder the flow or the movement of current in the circuit. That force of opposition is what we refer to as resistance. Okay, so resistance is the force which opposes the flow of current through a circuit. So the force which opposes the flow of current through a circuit is what we refer to as resistance. Or in other words, you can say that it is the opposition to the flow of current in a circuit. The opposition to the flow of current in a circuit. The unit of resistance is ohms. So it is measured in ohms. It's measured in ohms. Ohms is actually a name of a person. Ohms. So it is written with capital O. The symbol of ohms is this. So take note of the symbol of ohms. Okay, so that's the symbol of ohms. So please take note of these definitions: potential difference, electromotive force, voltage, and resistance. We're going to continue by looking at Ohm's law. Ohm's law. Ohm's law. When you go through your past question, you come across the state the Ohm's law. State the Ohm's law. The Ohm's law states that the voltage across the terminals of a metallic conductor in a circuit is directly proportional to the current passing through it. Provided temperature remains constant. Okay, so that is the Ohm's law. It says that the voltage across the terminals of a metallic conductor in a circuit is directly proportional to the current passing through it. Provided temperature remains constant. So there is a condition there. It means that the voltage will only be directly proportional to the current if the temperature does not change or the temperature remains the same. What does it mean? It means that if the voltage is directly proportional to the current, it means that as the current is increasing, the voltage will also be what? Increasing. The reverse also holds. That is, as current is decreasing, the voltage will also be decreasing. So that is, as current increases, the voltage also increases. Now, from the definition, it says that the voltage is directly proportional to the current. Mathematically, it means that V is proportional to I. We've looked at definition of voltage. We say voltage is represented as V. We've also, when we started looking at this topic, we look at what current is. We say current is represented as I. In mass, this represents the sign for proportionality. So we say V is proportional to I. And anytime you have the sign of proportionality and you change it to equation, you introduce a constant. So from here, V is equal to K times I, where the K is constant of proportionality, where K equals constant of proportionality. Now, from experimental work, the constant here is actually equal to the resistance in the circuit. So from experiment, the constant of proportionality, that's the K, is equal to R, resistance in circuit. So it means that when you replace the K with R, your V equals R times I. So V equals R times I, which implies that V is equal to IR. So from the definition, the equation from the Ohm's law is represented as V equals IR. So if you come across this in OBG, the Ohm's law can be represented by the equation. The correct answer is V equals IR. And we're making use of this equation a lot when we start looking at calculations. So this is one of the important equations you shouldn't forget. V equals IR. In case you're supposed to make I the subject, your I becomes V over R. If you're looking for R, your R becomes V on I. Now, so let's look at graphical representation of this equation. So this involves a graph of your voltage on the vertical axis, so your voltage V is in volts, and then you have your current I in amperes. This gives a linear graph of this nature. And then if you are supposed to determine the slope of this, this is change in V against change in I. we have V1, you have I1, we have V2, you have I2. So your slope from this graph will be a change in what is on the vertical axis, that's change in V, against what is a change in what is in the horizontal axis, which is the current. So your slope here will be equal to change in V over change in I, and this will be equal to V2 minus V1 over I2 minus I1. So this the slope will be determined from a graph of V against I. In practical work, after determining the slope, one question they ask is, what is the significance of the slope? So from here, your slope is changing V. That's voltage over current. From here, you said that when you make R the subject, your R is equal to V on I. So change in V over change in I. So if you ask from this graph, what is the significance of the slope, or what does the slope represent? You say that the slope represents the resistance in the circuit. So here, the slope represents the resistance R in the circuit. Alright, so that is graphical representation of voltage against current, and then the interpretation of the slope from the graph. Let's talk about, or let's look at what we call ohmic conductors and non-ohmic conductors. So ohmic and non-ohmic conductors. So ohmic conductors when you say ohmic conductors, simply they are conductors that obey the Ohm's law. So a conductor that obeys the Ohm's law referred to as ohmic conductor. It means that for that particular conductor, a graph of voltage against current will show or will indicate a direct proportion between the voltage and the current. On the other hand, conductors that do not obey the Ohm's law, we refer to them as non-ohmic conductors. It means that a graph of voltage against current for those conductors will not indicate a direct linear proportion between the voltage and the current. Okay, so ohmic conductors, they are conductors that obey the Ohm's law. So it means that for any conductor obeying the Ohm's law, the graphical representation should be as indicated earlier. So any conductor that is ohmic, a graph of the voltage in volts against current in amperes should indicate a linear graph showing a direct proportion between V and I. At any point, the current increases as you move to the right, and the voltage increases as you move upward. So at any point, when current is at this point, you have the voltage here. When the current increases, the voltage also goes up. When current increases, the voltage goes up. So that's showing a direct correlation or proportion between the current and the voltage. So that's why I say that if V is directly proportional to the current, it means that as the current is increasing, the voltage will also be what? Increasing. So ohmic conductors show this relationship between the voltage and the current. Then let's look at non-ohmic conductors. As I said earlier, these are conductors. They are conductors that do not obey the Ohm's law. Let's look at some graphical representation. So if you have a graph of voltage against the current, and then you end up getting a curve this way, that should tell you that it's supposed to be a linear relationship. But if you get in a curve, then it means that that conductor is non-ohmic. Or if you have the curve this way, you also get a curve this way. It is also non-ohmic. Non-ohmic. So you may come across an OBJ question and say, which of the following represents an ohmic conductor? And you have these graphs indicating. And if you have a graph sloping downwards this way, it is still non-ohmic. Because this does not show a direct proportion between the current and voltage. It is rather show an inverse proportion. So any of these graphs are actually what? Non-ohmic. Non-ohmic. This is the only one which is ohmic. So please take note of this. Alright, so this concludes Ohm's law. The next thing we're going to look at is to start looking at related questions or calculations. So, related questions. Now, before we start looking at some questions, as a recall, or summary. We came across certain relationships or equations when we were talking about connection in series and then connection in power. So for series arrangement or series connection, we came across these equations. The first one, if cells are connected or if resistors are connected in series, it said that the total current is the same as the current flowing through each resistor. So we came across this relationship. We say IT equals I1, it is equal to I2, it is equal to I3. Then in terms of voltage, we say the voltage is the total voltage, or what we call the effective voltage, is determined by summing up the individual voltages. So we say that VT is equal to V1 plus V2 plus V3. And then we say for total resistance in the circuit, RT is also the sum of the resistances of each of the resistors. So RT is equal to R1 plus R2 plus R3. So these were the equations we came across for series connection. And also for parallel connection, in terms of current, we said the total current is the sum of the individual current flowing through each of the resistors. So we said the total current IT is equal to I1 plus I2 plus I3. And then in terms of voltage, we said that the total voltage is equal to the voltage across each of the cells. So it's the same as the voltage across each of the various resistors. So your VT is equal to V1 is equal to V2, and which is also equal to V3. And then for resistors in parallel connection, the effective resistance or the resultant resistance, which is RT, is determined by the equation 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay. And then today we've looked at Ohm's law. You see from the Ohm's law, the voltage is equal to IR, current times resistance. So that becomes our equation 3. So we making use of the information or the equations we came across under series connection, the equations under parallel connection, and lastly, the equation from the Ohm's law. So these are the equations that will help us in our calculations. So let's look at our first question. So question 1. Question 1. Okay, so we have a circuit diagram consisting of two cells. One of voltage 2.0 volts and the other one with a voltage of 1.5 volts. It also contains two resistors with resistances 2 ohms and 3 ohms. And from this diagram, we are asked to determine the total resistance in the circuit and also the total current flowing through the circuit, the current flowing through each resistor, and then the voltage across the 2 ohm resistor. So you are calculating the total current, that is the IT in the circuit, and then the current flowing through the 2 ohm resistor, the one that is also flowing through the 3 ohm resistor. Now, whenever a circuit diagram is given, you've got to first of all ask yourself the arrangement of the components in the circuit. So this diagram contains two cells. So you ask yourself, what is the arrangement of the cells in the circuit? From here, I told you that a cell has two terminals, positive and negative. So positive, negative, positive, negative. The longer terminals are the positive and the shorter one the negative. I told you that in connections of cells, if the negative or the positive terminal of one cell is connected to the negative, as in this case, you have the negative terminal connected to the positive. If the cells are connected in that way, then we say that the cells are in series. The cells are in series. So if you are supposed to look for the total voltage in the circuit, that was not stated in the question. But before you can calculate for your total current, you need the total voltage in the circuit. For you to determine the total voltage in the circuit, you have to analyze as whether the cells are in series or they are in parallel. And from what I just said, because the negative terminal of one cell is connected to the positive terminal, it means that these cells are in series. So for series arrangement, how do you determine the total voltage? So you come across the information for series. You say for series arrangement, the total voltage is the sum of the individual voltages. So for us to get a total voltage here, it will be the sum of the individual voltages there. And then also, we have resistors, two resistors here. You ask yourself, the resistors here, are they in series connection or they are in parallel connection? We've looked at these arrangements already. So this is in series connection. So for series connection, how do you determine the total resistance? So this is also under series. So the total resistance is the sum of what? The individual resistances. Okay. So with that said, we can look at the solution now. The solution. So let's say let V1 equals 2.0 volts and V2 equals 1.5 volts. In terms of the resistance, let R1 equals 2 ohms and then R2 equals 3 ohms. Now for question A, we have to find the total resistance. So total resistance that's RT is what we are looking for. As I said, the resistors here are connected in series. So for series arrangement, your total resistance is the sum of the individual resistances. So it means that your RT here is equal to 1 R1 plus R2. So it means our total resistance RT will be equal to R1, which is 2, and then R2, which is 3. So that will be equal to 5 ohms. So the total resistance in the circuit is 5 ohms. Is 5 ohms. Now the second question says, if you look for the total current flowing through the circuit. Total current flowing through the circuit. If you remember this from the Ohm's law, it says V is equal to IR. I said that if you're supposed to make the I the subject, your I here will be equal to V over what? R. So for you to determine the total current, you need the total voltage and the total resistance in the circuit. If we've already calculated for the total resistance in the circuit, that's RT. So we are supposed to find the total voltage. That was not asked in the question, but before we can find the total current, we need the total voltage. So we look for the total voltage in the circuit first. So total voltage we don't know. But as I said, the cells here are in series, and for series arrangement, the total voltage is the sum of the individual voltages. So yeah, the total voltage VT is V1 plus V2. The V1 is 2.0 volts, V2 is 1.5 volts. You add that, that will give you 3.5. So the total voltage in this case is 3.5 volts. I've not underlined it because that is not one of the main questions that was asked in the question. But then, without it, we can't find the total current. So we have the total voltage now. We also know the total resistance. So we can look for the total current. So total current. So total current, that's IT. You don't know. But I'm saying that from Ohm's law, the voltage is current times the resistance. But we are looking at total, so you make use of total. So it means that total voltage will be equal to the total current times the total resistance. So if you make the total current the subject, your IT becomes the VT over the RT. If you do our substitution, the total voltage is 3.5 and then the total resistance is 5. When you point down your calculator, 3.5 on 5, that will give you 0.7. And the unit of current is amperes, so the answer becomes 0.7 amperes. So that is for the B. That's the total current flowing through the circuit. The total current flowing through the circuit. Now the C. Question C says that you should determine the current flowing through each resistor. Current flowing through each resistor. I told you that for series arrangement, the total current is the same as the current flowing through each of the resistors. So here is the same total current here. It gets here, it flows through the 2 ohm resistor. The same total current flows through what? The 3 ohm resistor. So the current flowing through your R1, that is the 2 ohm resistor, is the same as the total current. It should be 0.7 amperes. Similarly, the current flowing through the R2, that is the 3 ohm resistor, will be equal to the IT, which is also 0.7 amperes. So current flowing through 2 ohm resistor. Since 2 ohm is the R1, I'm calling that current as I1. Don't know. We are saying that that current, your I1, is equal to the IT, which is equal to 0.7 amperes. Similarly, current flowing through 3 ohm resistor. The 3 ohm resistor was labeled as R2. So the current flowing through, I'm leaving as I2. You don't know. I'm saying that your I2 is also equal to the total current IT. So that is also 7 amperes. Okay. So the current flowing through each of the individual resistors is the same as the total current flowing through the circuit. Flowing through the circuit. Question D says, she determined the voltage across the 2 ohm resistor. So you are looking at the voltage across the 2 ohm resistor. You are looking at this. So if this R1, you are looking at V1, the voltage across the 2 ohm resistor. We also have the voltage here, which is the V2, across the 3 ohm resistor. So we've identified the current flowing through it. This is as IT. We know this resistance already, that is 2 ohm. So from V equals IR, we just use this equation and then we look for the voltage. So the voltage across the 2 ohm resistor will simply be the current flowing through the 2 ohm resistor and then the resistance. So voltage across 2 ohm resistor that is V1. We don't know. But as I said, V equals IR. So from here it means that V1 equals I1 times R1. So my V1 is equal to I1. The I1 we said is 0.7. And then the R1 is the 2 ohms. So times 2. And that will give you 1.4 volts. Okay. So that's the voltage across the 2 ohm resistor. Similarly, if you were supposed to find the voltage across the 3 ohm resistor, then your V2 will be equal to the current flowing through this resistor, which is I2, and then the resistance, which is R2. So your V2 here will be equal to I2 times R2. We said the I2 is also 0.7, and then the R2 is the 3. So 0.7 times 3, that will give you 2.1. 2.1. Okay. And if you add the two voltages, the total voltage here should be the sum of these two voltages. So I'm saying that if you do your calculation, your V2, supposing you're supposed to find the voltage here, the V2 be I2 times R2. I2 is also 0.7, R2 is 3. So that will give you 2.1 volts. And I'm saying that the total voltage should be what? The sum of the individual voltages. So if you add this one and this, it should give you the total voltage that we determined earlier on as 3.5. We had the total voltage as 3.5. So if you add this 2.1 plus the 1.4, that will give you 3.5. That will give you 3.5. Okay, so that ends the solution to question 1. We're going to look at another question before we end today's section. Okay, so question 2. We have this diagram, and then from the diagram we have to find the effective voltage, effective resistance, effective current, and the current flowing through each of the resistors. That's the 2 ohm resistor and then the 3 ohm resistor. So over here we have 2 components. We have cells, and then we also have resistors. We have 3 cells here. Each of the cells have a voltage of 2.0 volts. And just as in question 1, the cells here are connected in series. Over here too, we have 2 resistors, 2 ohms and then 3 ohms. By comparing this diagram to that of question 1, in question 1 the resistors were connected in series. But for question 2, the resistors are not in series, they are rather in parallel connection. The cells, however, are in series, but the resistors are in parallel. Okay. Now let's look at the solution to the question. We said let V1 equals 2.0 volts. All the voltages are the same. V2 2.0, V2 2.0 volts, V3 is also 2.0 volts. We have 2 resistors, R1, 2 ohms, and then R2, 3 ohms. Question A says we should find the effective voltage. Your effective voltage, if you can't cross the word effective, is the same as the total, is the same as resultant. So if you hear total voltage, effective voltage, resultant voltage, they all mean the same thing. So our effective voltage is the same as the total voltage, VT. I said the cells are in series. So because the cells are in series, the total voltage here will be the sum of the individual voltages. So the total voltage here is equal to V1 plus V2 plus V2. And that will be 2.0 plus 2.0 plus 2.0. So the total voltage here is 6.0 volts. Then the B, effective resistance. RT is the same as the total resistance. Yeah, we said the resistance are in power connection. So for power connection, we use the relation. If you come here, So for power connection, we say the total resistance is determined as 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. So here, you only have two resistances. So 1 over RT is equal to 1 over R1 plus 1 over R2. So you have 1 over RT to be equal to 1 over R1, it is 2, plus 1 over R2, it is 3. One over RT becomes, if we add this, that will give you 5 over 6. 5 over 6. So 1 over RT equals 5 on 6. But you are looking for RT. So you find the reciprocal of what is on the left and then what is also on the right. Reciprocal of this means that your RT goes up and then the 1 comes down. So you end up getting RT over 1. RT over 1 is the same as RT. So this one too, you find the reciprocal, meaning that the 6 will go up and the 5 will come down. Or if you want, if you cross multiply here, you get 5 RT. This times it will be 5 RT, and then 6 times 1 is 6. You are looking for RT, so you now can divide both sides by 5. This cancel. So your RT is 6 over 5. So that's it. That's why I said that if you find the reciprocal of this, you also find the reciprocal of this. So RT becomes 6 over 5, as in this case. So yeah, it implies that RT is equal to 6 over 5. Six on 5 is the same as 1.2 ohms. So the total resistance there is 6 on 5, which is 1.2 ohms. 1.2 ohms. Question C is asking for the effective current. The effective current is the total current. As I said, for you to find the effective current, you always make use of the Ohm's law. It says that V is equal to IR. And yeah, so we are dealing with total. So your total voltage will be equal to the total current and the total times the total resistance. So if you make the total current the subject, that will be the total voltage over the total resistance. The total voltage is 6.0, it has 6.0, and then the total resistance we had 1.2. That should give you 5. So our total current here is equal to 5 amperes. Good. Now the D are current flowing through 2 ohm resistor. Our 2 ohm, I label it as R1. So the current I'm also labeling that as I1. So if you look at the diagram, this is your total current. Don't forget, your current always flows from the positive terminal towards the negative. So your total current flows. It gets to this junction. There's a junction here. Some of the current will flow through this, the 3 ohm, and some also flowing through the 2 ohm. So this is R1, this is R2. So the current here, I1, some also pass here, that is I2. These two, so I1 is passing through the 2 ohm, I2 is passing through the 3 ohm. They combine again, and then they form the total current. It flows through this, and then it comes here and then divides. Okay, so your I1 is the current flowing through the R1, that's the 2 ohm resistor, and the I2, the current flowing through R2, which is the 3 ohm resistor. So how do you determine that? So here, this is not similar to what we did for question 1 with the series. For question 1, we said because the resistors were in series, it's the same total current that flowed through each of the resistors. So he said that the I1 is equal to IT, the I2 is also equal to IT. But from what I just explained, it's not the same. This total current gets here, and then it divides into two. Some of the current pass through the 2 ohm, and then some also passes through the 3 ohm. And later, they combine again to form the total current. Okay, so how do you determine the current flowing through each of these resistors? Don't forget that we said for power arrangement of resistors, the total voltage is the same as the voltage across each of the resistors. So if you come here for power connection, total voltage for resistors is equal to the individual voltages. So we have determined the total voltage here, which we said is 6 ohms. So it means that that total voltage is equal to the voltage across the R1 is also equal to the voltage across what? The R2. So the voltage here is equal to the 6 volts. The one here is also equal to what? 6 volts. So once you know that voltage, you can determine the current. So using the Ohm's law, V is equal to IR. You make I the subject. So first of all, voltage across two ohm resistor. Our 2 ohm is R1, so that's V1. It's equal to the total voltage, which is 6 volts. So we can now find the current. So current flowing through 2 ohm resistor. That is I1. But for Ohm's law, your V1 will be I1 times R1. So if you make I1 the subject, that will be V1 over R1. We said the V1 is the total voltage, which is 6.0. And then the R1 is a 2. So 6 divided by 2, now give it 3 amperes. So your I1 is equal to 3 amperes. So that's the current flowing through the 2 ohm resistor. And that's DII. This one too. The voltage across the 3 ohm resistor, that is V2. It's also VT. So that is 6.0 volts. You can look for the current flowing through. Flowing through 3 ohm resistor. That's I2. So just like the DI, using the Ohm's law, our V2 will be I2 times R2. So if you make I2 the subject, your I2 will be V2 over R2. Our V2 is still the same as the total voltage, which is 6, and then the R2 is 3. So that'll give you 2 amperes. So the total, or the current flowing through the R2, the 3 ohm resistor, is 2 amperes. And as I was explaining, it is this total current that split to form I1 and I2. So it means that your IT here is equal to your I1 plus I2. The I1 we calculated is 3 ohms. And then the I2 we calculated is also 2 ohms. So your 3 plus 2, that will give you 5, which we actually had as the total current. So the total current here is 5. And then the I1 we had 3, the I2 we had 2. If you add these two, that should give you the total current is 5. Okay, so this is how you determine the current flowing through each of the resistors connected in parallel. So this is quite different from when the resistors are in series. That one is so simple. Once you know the total current, we said that total current is equal to the current flowing through each of the resistors. But for parallel connection, the currents are different. And this is how you determine the current flowing through each resistor. You just determine the total voltage. As I said, for parallel connection, the total voltage is the same as the voltage across each resistor. And we have that total voltage to be 6. So if you want the current flowing through this resistor, you just divide the total voltage by this resistor. That is 6 over 3. And that will give you 2. Similarly, the current flowing here will be the total voltage, which is 6, divided by the 2. That will be 6 over 2, which will give you 3. Okay, so please take note of this, how to determine current flowing through resistors connected in parallel connection. Okay, so this brings us to the end of question 2, and for that matter, the end of today's section. God willing, tomorrow we're going to look at more questions. I believe that tomorrow, by the time that we are through with the next batch of questions, you get more understanding of the calculations. Enjoy the rest of the day. Until we meet again, make sure you continue to study seriously.